Resistance is rho times L divided by A. L is the length of the wire. A is the cross-section area. Rho is a quantity called the resistivity. Good conductors have a very small number for resistivity. Bad conductors have a very high number for this resistivity. And this is the resistance of a piece of wire. Okay? I'm going to show a demonstration with this. This is a carbon filament lamp. This is a seriously like old school carbon filament lamp. And this is Lewis Latimer. Lewis Latimer is a person I'll come back to later. But I'll look at a carbon filament lamp here. And I've got some bulbs in the front of the room. And I'm going to start off with this one. And this is a carbon filament lamp. It's a real old one that I got. Okay, and I'll plug it in here. And when I turn it on, it's going to come on, and it takes it a second to get it to come up to full brightness. And that's actually one of the problems with it. If I touch this, it takes it a long time to come up to full brightness. And if I make it a bit brighter, now we can see the filament. And you can see it's kind of a long, loopy structure, right? And it has to be a long piece of wire. Well, that was a problem with the bulbs. They're kind of like hard to make, and carbon isn't exactly sturdy. It's also hard to make into a shape like that. That was Edison's big problem, is how can you make a filament which is made out of carbon? The whole reason for choosing carbon is because it's really resistant to high temperatures, and this has to be very, very toasty. But ultimately, you would like to do this with metal. And so you had people in his laboratory working on this, including Lewis Latimer was someone who worked on this problem. And Lewis Latimer was one of the people who was able to come up with a strategy for being able to do this with metal filaments. And if you want to do this with a metal filament, it's much easier because making a metal wire is much easier than making a carbon wire. But there's a big problem if you're making a metal wire, and that's this. That piece of carbon filament, it's big. You could see there was a big length of wire there, and it's hard to get inside the envelope. But look, if I'm going to replace carbon with something else, something metal, what do you think about the resistivity of metal compared to the resistivity of carbon? Higher or lower? It's a really much good conductor, metals. Much lower resistivity. If the resistivity goes down, you either have to have a wire which has a much smaller area, so you have to have really thin wire, that's going to be hard, or else you have to have really long wire, okay? And so they had to come up with a way to kind of achieve that. Now I want to do a calculation. 100-watt light bulb carries a current of 0.83 amps at the normal operating voltage of 120 volts. A, what is the resistance of the filament? B, if the filament is made of tungsten wire of a diameter of 0.035 meters, how long is the filament? Okay? And here's a bulb, and you can see, if you look at this one, the wire looks like it's kind of about, I don't know, it's about that long. Let's do an electrical calculation based on what we know the wire is made out of and figure out how long is it actually. And let's go ahead and do that. We do two stages to the process. It's a 100-watt bulb, carries a current of 0.083 amps at the normal operating voltage of 120 volts. What's the resistance? Well, resistance, delta V divided by I. We reorganize our basic equation, make it look like that. What's the voltage across the bulb? 120 volts. And what's the current? 0.83 amps. So if I work that out, I get a resistance of 144 ohms. That's the unit that we use for it. 144 ohms. Question, if the filament is made of tungsten wire of diameter 0.035 millimeters, how long is the filament? Well, remember, we said the resistance of a wire was equal to rho times L divided by A. What is the resistance of the wire? 144 ohms. And that's equal to rho times L divided by A. Well, the resistivity is a property of tungsten. And at the temperature at which the filament operates, that's 5.0 times 10 to the minus 7th ohm meters. And the area I can get, because I know the diameter of the filament, the area is pi r squared. The radius is 0.0175 times 10 to the minus 3rd meters. So I can work out the area of the filament. The only thing I don't know in this equation is the length. And I can solve for it. And if I do that, I get the length of the filament, 0.28 meters, or 28 centimeters. And 28 centimeters is It's about this big. Okay? It's about this big. Now, in fact, this light bulb isn't a 100-watt bulb. It's a 40-watt bulb. Okay? Now, if you want to go from a 100-watt bulb to a 40-watt bulb, think about this. You have to have less power. If you want less power, more or less current. Less current. If you want to have less current, how do you want to change the resistance? Increase the resistance gives you less current. Okay, and if I want to take my wire and I want to make its resistance be less, what do I have to change? What's the easiest thing that you could change about your wire to make the resistance? I'm sorry, you have to increase the resistance. If I want to take the resistance and make it be more, what's the easiest thing to change in this equation right here? The length, just make it longer. 100-watt bulb, the filament's about this long. 40-watt bulb, the filament's about this long. Oh, you're saying, Brian, that's crazy talk, because look at that light bulb. I can see it. It's like this long. Oh, but if you took a really, really close-up view of that light bulb, here's what you see. It's coiled. And it's not just a coil, it's a coil of coils. Have you noticed when you look at a light bulb close-up, you can tell it's coiled? And if you could really seriously get in there and small and see the scale of it, it's actually the big coil structure you see is this, but those are made up of smaller coils. So this light bulb, the filament's this long. But it's actually this much length which is packed into that envelope. So it's really quite an interesting technical problem in order to figure out how to do this. And it's a remarkable piece of manufacturing to do these incandescent light bulbs. And I feel bad for incandescent light bulbs because they're getting a bad rap these days. Oh, sure, it's energy inefficient, planet destroying, and all of that. But doggone it, there's a piece of wire this long, and it's in that piece of glass like that. And so it's kind of cool.